Hello everyone, this is Mrs. Locust and I will be taking you through Unit 8A and also 8B as well. So all of Unit 8 you're going to hear my voice for days on end. Aren't you just so super pumped about that? I know I am. So let's get started, shall we? So Unit 8A is regarding polynomials. And remember, a polynomial is something that is made of multiple terms that's separated by plus or minus signs, like 2x the third plus 3x squared plus 4x plus 5. This would be a polynomial of degree 3 with 4 terms. And what we're truly focusing on in this unit is polynomial functions of a higher degree. Now, Unit 7, we focused completely on anything that was x squared or a quadratic. And now we're expanding our horizons to anything that's beyond a quadratic, a cubic, a quartic, something to the 5th power, anything higher than that. And so I think a perfect transition to that is by looking at the first example. Find a polynomial function that has the given zeros, x equals 0, x equals 2, and x equals -1. Now, because there are 3 zeros, I am going to guess that this is going to be a cubic function because 3 zeros usually leads to something that started with x to the third. And we'll talk about that more a little later. So what we need to do on these problems is think backwards. So if you think about all of the factoring and all of the solving we just did in Unit 7, if I get an answer of x equals 0, if you think about all the parentheses that we've done with factoring, everything in the end always equaled 0. So think of it backwards. If I have a root of 0 that came from x, just x, because you said x equal to 0. If I got a root of 2, that means it came from x minus 2, because if I said x minus 2 equal to 0, that would get me 2. And if I got a root of x, or x equals -1, that came from x plus 1, and let me rewrite this because it's a little bit too close together. So that last one was x plus 1, and all of that equaled 0. So this so far is my polynomial in factored form, x times x minus 2 times x plus 1. But if I want to make sure that my answer is cubic, I can go ahead and multiply these out and then multiply by x. So let me keep the x there and let me do the distributive property or FOIL and get x times x squared plus 1x minus 2x minus 2. And then if I distribute my x in, I'd get x cubed plus 1x squared minus 2x squared minus 2x, which is even better, x cubed minus 1x squared minus 2x. And so if I set that equal to f of x, this could represent my polynomial function that I can see is cubic now because of the 3 roots. So that is one possible answer, but there's really infinite, because what you could do is multiply this by really any number you want. For instance, if I wanted function g of x, if I multiplied everything by 2, I'd get 2x cubed minus 2x squared minus 4x, and that would be another answer that would get me these 3 roots at the end of the problem. Rather than just focusing on roots though, this first section is about looking at the graph of polynomials, interpreting them, and understanding certain things, like, for instance, end behavior of a polynomial. So you're asking yourself questions like, as x goes to positive infinity, the right side of the graph, what does the graph do after that in terms of the y values? Does it go positive or to negative infinity? And as x goes to negative infinity, to the left side, what is the y value doing? Is it going towards the positives or towards the negatives? And so I'm going to be basing all of this on a few parent functions here. I'm going to be talking about something you're very used to, the parabola if it's right side up, the parabola if it's upside down, a cubic function, and a negative cubic function. So just to use these parent functions to help you understand what end behavior is, if you look at a quadratic function, the end behavior means what is the end of the function doing, not the middle. Well, if you look at this one, the end behavior would be arrows pointing up in both directions. As you're going to the left, the y values are increasing, and as you're going to the right, the y values are also increasing. Versus a parabola that has a negative in front. As the x goes to the left, the end behavior would be that the y is decreasing this direction, and as I go to the right, the end behavior is that that y is also decreasing. If I look at a cubic function, as I go to the left on the x values, the y values decrease. As I go to the right with the x values, the y values increase. So the end behavior are going opposite directions this time. For a negative cubic function, as I go to the left with the x values, the y values increase. As I go to the right with the x values, the y values decrease. And so what we could do is organize this information, but I also would like you to notice that the parabolas are anything with an even power, because this would generalize to anything with an even power, and this generalizes to anything with an odd power, because these are really x squared and these are x cubed. So sometimes what you'll see is a nice little chart made for you. I know other teachers like to use this, that helps symbolize what I've just said over here. So I'm going to make a little box, and I'm going to label the top lead coefficient, and I'm going to label the side degree. I'm going to make this little 4 by 4. And now on the top by lead coefficient, either your lead coefficient or number in front of your function is either going to be positive or it's going to be negative. And the degree of your polynomial can either be even or it could be odd. So again, like over here, your even function could be something like x squared, and your odd function could be something like x cubed. So if you think about these pictures over here, if you have an even function, like a parabola, and you have a positive number in front of the whole thing, the end behavior is that both sides were facing upwards. If you have an even function but the lead coefficient's negative, it flips upside down, so your end behavior would be both y values facing downwards. If you have an odd function like a cubic and you have a lead coefficient that's positive, your function's increasing, which means your end behavior is starting down and then it's rising, like this picture. However, if your cubic function is a negative in front, it is decreasing, so the end behavior starts up and then goes downwards. There will be multiple times that I ask you about what your end behavior is, and it is always a good idea to draw a picture first. A next piece of information is terns. And what terns represent is the relative extrema, relative maxes or mins, or the point where the graph changes from increasing to decreasing or decreasing to increasing. So again, let me generalize from something that you already know. So you're very familiar with a general parabola. How many turns does a parabola have? Well, a parabola only turns once at that vertex where it's going from a decreasing interval to an increasing. So this one has one turn. If I then next talk about a cubic function, so something like this, remember that turns are not just where it changes from increasing, decreasing, decreasing to increasing. It's also talking about relative maxes or mins. And if you look at this cubic function, you could say there's a relative max here and here, because that's when it's changing something, as you'll learn in calculus, something called concavity, but that's for a later time. So it looks like this one has two turns. So I notice when the degree is x squared, it has one turn. When the degree of the polynomial is 3, it has two turns. So if I use this generalization, it seems that the max number of turns of a polynomial is the degree minus 1. So we'll go from cubic to 2, squared to 1. So for instance, if I gave you an example, like if I want you to say how many turns does the polynomial 2x to the 7th minus 5x to the 3rd have, you'd look at the highest degree and say that there has to be at most 6 turns. Now it's possible that the polynomial may not have exactly 6 turns, but that is the maximum that it could absolutely have. So next we're going to be talking about real zeros, meaning real zeros mean the ones that actually exist, or non-imaginary. And yes, we will be dealing with imaginary. I know some of you might have been fretting and saying, oh, I have to deal with imaginaries. Don't worry, you'll get your chance to do so. So what real zeros are is something we've been working on so much already, that you're finding your x-intercepts, or the location where the graph touches the x-axis or crosses it, and you can identify a polynomial's number of roots by using the zero product property. And also, something good to point out here is, again, something I mentioned briefly earlier, that the number of possible real zeros is equal to the degree of the polynomial. So if I, again, make up an example like 2x the fifth minus 4x cubed plus 2x, if I give you this polynomial, the number of possible real zeros or roots would be 5. That's the total possible, but just like the terns, it is possible that some of them could be imaginary, so it's the max number of real zeros here. Other terms that you're familiar with are going to help us out in just a minute are the y-intercept, or the location where the graph crosses the y-axis. And I would consider starring this because it's so easy to forget. To find the y-intercept, remember that x is really 0. So you could just plug x equals 0 into the equation and you can get the y value out, which would get you your y-intercept. The number of terms we've already talked about is the groups of numbers and variables separated by adding or subtracting. The lead coefficient is the coefficient of the term with the largest degree, and so that kind of also leads me that it's a good idea to consider putting every one of your polynomials in standard form still. The domain is every possible x values, range is every possible y value. The degree, as we talked about earlier, is the largest exponent, and the last thing, multiplicity, represents if a graph either bounces at the x-axis or if it goes through the x-axis. And it has to do with the powers that are on there. And we'll get into that into a little bit more detail. But what you need to know for now is that if there's an even power, the graph is going to bounce. And if it's an odd power, it's going to cross directly through the x-axis. So let's do at least one of these in this video. Complete the following information about the given function, and then use that information to graph the function without a calculator. So, the degree of this polynomial. Well, the highest degree that I see is 4. Number of terms. Terms separated by a plus or minus, 2. The leading coefficient, the number in front of the highest degree, 3. The end behavior. Well, this is an x to the 4th function, and we're going to be learning about more about what that looks like, but I would say that treat this like the x squared, that because the 3 is positive, my graph is going to be facing upwards. There's something going to be going on in the middle. I'm not sure exactly what, but I do know that the other end behavior is going to be sticking up as well, because you treat it like a parabola. So my end behavior would be 2 arrows facing like this, or we could write end behavior in a nice new notation. So what we could say instead is as x goes to negative infinity, or as x goes to the left, my graph is going upwards. So that means as x is going to negative infinity, my y is going to positive infinity. As x is going to positive infinity to the right, y is also going to positive infinity. I know that on a test or quiz, I am eventually going to prefer this notation that I'm boxing in green. These blue arrows are good at first to help you understand, but this notation is what I know I'm looking for. I'm sure that's true with Ms. Schwartz as well. Possible extrema. That is the degree minus 1. So for this example, because the degree is 4, that means that my number of terns must be 3 possible ones. 4 minus 1. My number of possible zeros is the same as my degree of my polynomial, so that means my possible real zeros would be 4 of them. So here is where I'm going to pause this video because I'm running out of time. So in the next video, what I will do is I will find the zeros, I will find the y-intercept, and I will use all this information to graph on here. And we'll do a couple more examples. Thanks, everyone.